In today's video, I'm gonna go over the topic of complex numbers, and I'm gonna start with the basic concept called imaginary number. Let's say we got an expression that looks like x squared plus 1 is equal to 0. So if we subtract 1 from both sides, this gives me x squared is equal to -1. Okay, so in this case, if you notice, a square of any number, even if it's a negative, the answer is always positive. For example, let's say if I got a -2 and I square it, I'll get +4. If I got -3 and if I square it, I'll get +9. What in this case, we are getting a square of a number equal to negative value. So in this situation, we introduce a concept called imaginary number. Okay, imaginary numbers. And that number, we represent it by a letter I called iota. Okay, so that case, imaginary number can be written as I square equal to -1, or can say I is equal to square root of -1. So whenever we get a negative number under a square root, we call that number an imaginary number. So in this situation, like as this expression gave us. Okay, so that means I square is equal to -1. And if I have to write I cube or iota cube, this gives me, I can rewrite it as iota square into iota. So iota square, which is -1, so this value will be -1, so negative iota. Okay, and let's move to power 4. What will happen there? So we can rewrite it as iota square, so that means -1 times -1, which gives you +1. So this is how you can find the value of this imaginary number if there is a power on it, keeps increasing and so on. So I'm gonna give you a trick that you can use for any power that goes to I. So let's say I raised to power n, and n is greater than 4, and we know if I raised to power 4, it is 1. So whenever it is a multiple of 4, that's gonna give you 1. Okay, and if it is not, how to find the value of this number? So let's go over that trick. So what we're gonna do here, so let's say this I raised to power n, we're gonna divide this n by 4. So whatever remainder we get, again, so this is a power n, it can be any big number, you don't know. And sometimes they ask you, let's say I raised to power 150, what is the value of this number now, this imaginary number now, or rewrite it. Okay, so this is big number, can be bigger than that, or like 199, 2000, 1 million on the top, whatever, I don't know what. That's how you can solve it. So raised to power n, and n is greater than 4. What you need to do, divide this n by 4, and you get some remainder. So this will give you, let's say, a remainder r. Then this I raised to power n is basically equal to I raised to power that remainder. So whatever remainder you get over there. Okay, so let's do this example over here. So iota 150, and this will rewrite it or find the value of this imaginary number here. So what we're gonna do, 150 again greater than 4, I'm gonna divide it by 4. So that gives me 4 times 3, 12, 3, and I bring down 0. 4 times 7 is 28. so I left with 2. So this 2 is my remainder. So this I raised to power 150 is basically equal to I raised to power 2. This is equal to -1. I hope that makes sense. Okay, so let's say you got I raised to power 999. There are different ways to do it, like you can write it. Oh, sorry. Let me fix it. So I raised to power 3 power 333, and you can do this way too. I raised to power 3 is, as we did in previous slide here, is negative I. So negative I raised to power 333. So this is gonna go a little longer, but the way I'm telling you is much easier and faster. Okay, so you got iota raised to power 999. So what we're gonna do, we're gonna divide 999 by 4. This gives me 8, 1, bring down 9, 4 times 4 is 16, 3, 9, 4 times 9 is 36, 9 minus 6 is 3. So 3 is my remainder. So this basically is equal to iota raised to power 3, which is iota square into iota. Iota square is -1 and iota is just iota. So answer is just negative iota. So that's how you can solve these kind of imaginary numbers. Okay. So let's do a couple more examples on this topic of imaginary number. Then we're gonna go over what are complex number, because we need to know this imaginary number. Then we can write a complex number. Okay. So let's do one more example. In this case, I got I raised to power 18 plus 1 over I raised to power 25. And again, it's not I, it's iota. I keep saying I, but you can you can get it. Let's do this one. Okay, so same thing we can use. Iota raised to power 18. If I divide 18 by 4, 4 times 4 is 16, gives me 2 as a remainder. So this I raised to power 18 can be written as I raised to power 2 plus 1 over, so I raised to power 25, right? So 25 divided by 4 gives me 1 as a remainder. So I raised to power 1 and power 3 over there. Okay, so then what we can do here, so this I square or iota square is a -1. I want to bring this iota to the top. So what they do, multiply by iota here. So on the top I left with iota, and the bottom I left with the iota square, which is -1 raised to power 3. So this gives me -1 minus iota power 3, or can be written as negative out, so 1 plus iota cube. And we're gonna use the formula, or the what they call it, identity, a plus b cube, okay, which is equal to a cube plus b cube plus 3ab into a plus b. Okay, so that's what we're gonna use in this case. So negative is out, so we got a cube is 1 cube, then we got iota cube, then we got 3 times 1 times iota into 1 plus iota. There you go. So let's rewrite it again. So -1, so 1 cube is 1. Let's keep this as iota cube. So 3i times 1 gives me 3i, or 3 iota. So 3 iota into iota gives me 3 iota square. Alright, so let's rewrite this again. So this iota cube is basically negative iota. We wrote it in previous slide. So 1, or let's do it, iota square into iota plus 3i plus 3i square. So negative, so 1, Iota square is a -1, so negative times positive gives me negative. And this is iota, and here you got plus 3 iota, and iota square gives me negative, so you got -3 iota over here. Okay, so let's do more math or more algebra. So this 3i, sorry, this is not supposed to be I there, just 3. Okay, so negative iota plus 3 iota gives me positive 2 iota, and 1 minus 3 gives me -2. So I got -2 plus 2 iota. So let's distribute this negative. So this gives me 2 minus 2 iota. So that's your answer here. Alright, so that's how you can solve the problem that looks like this. Okay, so let's move to the next topic. So that's where I'm gonna go over complex number. Okay, so let's say if you got a and b, and both are, let's say a and b are two real numbers, then a number of the format which looks like a plus iota b is called a complex number. So here this a is a real part and this is the imaginary part. So we got a combination of real and imaginary. So this combination of real and imaginary number is called complex number. Okay, and every real number is a complex number. Let's say 2, right? It can be a complex number. How? Because 2 can be written as 2 plus iota 0. There you go, that's a complex number. So every real number is a complex number. Okay, and then we need to learn a topic called inverse of a complex number. So you might see problems, they'll ask you problem on find the inverse of a complex number. So let me write it down here. Inverse of a complex number. Okay, so inverse of a complex number. If the product of two non-zero complex number is 1, let's say you got one complex number z1, the other one is z2, and it says if the product of two non-zero complex number and the product of these two number is equal to 1, then each one is the multiplicative inverse of the other. Okay, so let's say this is the case, then z1 is multiplicative inverse of z2. Okay, multiplicative inverse of z2, and vice versa. That means z2 is a multiplicative inverse of z1. All right, so let's do a real example. They said find inverse or the multiplicative inverse of 2 plus 3i. Okay, so what will be the multiplicative inverse? That will be 1 over 2 plus 3i. See, if you got 2 plus 3i and you multiply it by 1 over 2 plus 3i, then answer is 1. See, this is the situation here, condition there. So this number here is a multiplicative inverse of this one. So 1 over 2 plus 3i is a multiplicative inverse of 2 plus 3i. And we can rewrite it as, so that's where we're gonna use another concept. It's called conjugate of a complex number. Let me write it here. Conjugate of a complex number. What is a conjugate of a complex number? Let's say you got a complex number z is equal to a plus iota b. Then the conjugate of z is denoted as z bar is equal to a minus iota b. So change this sign to minus. So that's how you can define the conjugate of a complex number. Okay, so in this example, that's where they said find the multiplicative inverse of this number, which is 1 over 2 plus 3i, and we can rewrite this in standard form of a complex number. Then what we need to do, we need to multiply this number by the conjugate of the denominator, so which is going to be 2 minus 3i and 2 minus 3i. Multiply and divide. So this gives me 2 minus 3i over so here we can use the identity again, so which is a plus b into a minus b, so that is equal to a square minus b square, or you can just distribute or FOIL those factors to get your equation. Okay, so if we just remember the formulas, super quick. So that case we got 2 square gives me 4 minus 3i square. So 3 square is 9, then I square. Okay, so 2 minus 3i over 4 plus I square is negative 1. So negative into negative is positive 9. So this is equal to 2 minus 3i over 19. Oh, sorry, 13. And this can be rewritten as 2 over 13 minus 3 over 13i. So this is a standard form of a complex number. See, the first part is real part, the second part is imaginary part. So you can say this is also a multiplicative inverse of 2 plus 3i. Alright, so let's move to the next topic. So this is called modulus of a complex number. Okay. Modulus of a complex number. Okay. So let's say I got a number, a complex number z is equal to a plus ib, and let's represent this number on a complex plane here, or argand plane they call it. So there you go. This direction is y, this direction is z, and my number is, the complex number is here, let's say p a comma b. Okay, then this length in this direction is my a real part, and this is my imaginary part b, and so this distance from the origin to the complex number is called the modulus, or the absolute value z, which is equal to square root of a square plus b square. You can also use the distance formula, you'll get the same result. So this modulus of z is the distance between a complex number z and the origin. Okay, and there will be problem, they'll ask you to find a modulus of a complex number. Okay, and after that they might ask you argument of a complex number or the amplitude of a complex number. Okay, so let's go over that topic now. Let me write it here. Argument. So argument of complex number. we're gonna go over some examples too. So I'm just covering the topic here, just the concept. So we'll be solving some examples too. Okay. So argument of a complex number. So let's draw the complex plane, or again they also call it Argand diagram. Okay. So I got complex number here. Let's say let me write it. Z is equal to 2 plus 3i. Okay, so this point P here will be 2 comma 3, 2 this way and 3 this way. Okay, and this is our modulus. This length from origin to the complex number can also be called a vector. Okay, so this is 0 0 here, the origin, so this direction is x, this is y, so this is 2, this is 3. All right, so what is the argument of this complex number? So that's the question. So argument is the angle made by this vector or made by this modulus of complex number and a positive real axis. So this is my positive real axis and this is my modulus or the vector of a complex number. Then this angle over here, I say theta, is called the argument of this complex number. Okay, and how you can find it? So we need to use some trigonometry here. So tan theta from here, this is 90 degree, is going to be 3 over 2. Therefore we got theta is equal to tan inverse 3 over 2. So this angle over here is called the argument. And the fun fact or the important thing to remember is argument of a complex number is not a unique value. Okay, so argument of a complex number is not unique. That means the value can change. The value is you can get multiple values, different values. Okay, because this angle, one rotation is 2 pi. If I do another rotation, that's multiply by 2. Another rotation multiply by 3. 3 times 2 pi, 4 times 2 pi. Okay, and if the argument of complex number, let's say, let's write argument in general. If the argument of complex number is theta, okay, it is also be theta plus 2n pi. See, it can be any value. So if you change n, if n is 0, so number of rotation, let's say, then it is just this value theta. N is 1, then is theta plus 2 pi, and then 4 pi, 6 pi, 8 pi, and so on. So you can say any two arguments, so any two arguments differ by 2n pi. Okay, and let's say if the argument of a complex number is unique, then it is called principal argument. and also called amplitude, because the value is not changing. Okay. In that case, the value of the amplitude will lie between negative pi and positive pi. All right. So now let's go over how we can write the general values of arguments. Okay. So I'm gonna go over that topic here. So the argument of complex number z is equal to a plus ib, and the complex number in polar form can be written as r into cos theta plus I sine theta, right? So in that case, a is equal to r cos theta and b is equal to r sine theta. Okay. So let me write few values over here. Let's draw a diagram so that'll make more sense to you guys. Okay, so I got a number over here, say a comma b. Okay, then this is my modulus. So it is there. Then we draw a perpendicular, and this angle is my argument theta. And then we are in this side, let's say b, and go to the origin. And let's say this value is theta here. Okay, and b is negative a comma b. You can draw a perpendicular. Then you go to this quadrant here, got c minus a comma minus b. Let's say this angle is theta here. Okay, then you go to this quadrant d, which is a comma minus b. Then this angle is theta here. Now we're gonna write the principal value of an argument of a complex number. So argument value will be different in different quadrants, right? So this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So if the complex number, let's write number 1, if complex number z lies in the quadrant 1, the first quadrant 1, okay, then the argument of that function, that complex number is equal to this value here, this angle theta. Okay, now let's do, if this complex number lies in quadrant 2, then the argument is equal to pi minus theta. What is the value of angle here? So this is my complex number here in quadrant 2 here. Then this angle, you start from here. So this is my argument. Remember, argument was the angle made by this vector with the positive x-axis. So this is my positive x-axis. Okay, so the angle between positive x-axis and the vector of that complex number, which is this line over here. So this angle is, the total angle is pi, and you take out this theta, so pi minus theta will be the argument. Let's go to quadrant 3. If the complex number lies in the quadrant 3, then the argument is going to be, what will be the angle? This is my positive axis, so go from here to there. You can write it like this. That is going to be negative pi minus theta, because we are moving in opposite direction. Normally it is this direction, so we are going the clockwise, otherwise always anti-clockwise direction. Okay, so negative of pi minus theta. Now let's say if the complex number lies in quadrant 4, then the argument is going to be, see, this is my complex number here, and this is the vector. Then this angle going from here to there, this angle which is theta but in opposite direction, so negative theta will be my argument. So there is another case we can look at. This A can be positive, can be negative, right? Same thing with this B, can be positive, can be negative. Then what will happen to the argument? So let's go over that now. If complex number Z is purely positive real number, then the argument Z is going to be 0. For example, let's say if I got a complex number 2, what did I wrote? Let's say I got 2, just 2, which is 2 plus I 0. So in this case, this value 2 lie along my positive x-axis somewhere. Let's say here is 2, and y value is 0, so my complex number is here, and then the vector is also here, and the angle between a positive x-axis and the vector or the modulus of complex number is the same axis, and the angle between them is 0. I hope you understand it or you get it. Okay, so let me write it here. Okay, so x-axis, y-axis, our complex number is 2, which can be written as 2 plus I0. So how we can represent this on this complex plane? So the first number, real value, is the value along x-axis. Let's say 1, 2, so it is here. What is the value of b, the imaginary part? It's not there, just 0. So our complex numbers stay over here, and this will be my modulus, or this will be my vector from origin, and argument is the angle between the vector and a positive x-axis. So in this case, it's the same axis, the angle is 0, there's no angle. All right, that's why the argument is 0. Now if complex number is purely a negative real, then the argument is going to be, what will be the argument? Let's say it is negative 2 now, right? Negative real. So negative 2, I0. In that case, negative 2 will be on this side. So let's say it is here, right? Then this is my vector here, and positive x-axis is this side here. So the angle between a positive x-axis and the vector is going to be pi. So the value is pi here. Make sense? Okay. Let me try it here. So negative 2 is on this side, right? So my complex number is here, but there is no y value. Imaginary part is 0, gonna stay here. So origin is here, so vector is origin to the complex number, and the angle between this positive x-axis and this vector, this is x, this is y, this is pi radian. All right, so let's do, if complex number is purely positive imaginary, what will happen to the argument? Let's do that. So I'm gonna make some space here to make the diagram. Okay, so positive imaginary. Okay, so how you can write positive imaginary complex number? That means the real part is 0, but this is 3i, right? So how you can draw it? So if I draw it here, okay, so x and y. So x value is 0 when the complex number is purely positive imaginary number, then x value is 0. There is no x value. What y value is 3, the b value is 3, so we're gonna move in this direction 3 units, 1 2 3. So my complex number is right here. Okay, so what will be the vector, or what will the modulus? The distance from the origin to the complex number. This is my 0 0 origin. Okay, and what was the argument again? The angle between positive x-axis and the vector. How much is this angle? 90 degree, or pi over 2. So the argument is going to be pi over 2. Okay, so the last case is if the complex number is purely negative imaginary. So if it is negative imaginary, what will be the argument here? Let's draw the diagram here again. Okay, so if it is negative imaginary, I'm drawing this place a little bit. There you go. So we got our axis, x-axis, y-axis, and number is a negative imaginary. So let's say negative 3 iota, which is 0 minus 3 iota. So x value is 0, but y value is negative 3. So we are moving in negative direction. This is 0. So 1, 2, 3. So my complex number is here, and the vector or the modulus is this vector, and the argument is the angle between the positive axis and the vector of a complex number. So this angle, which is again pi over 2 but in opposite direction, so negative pi over 2. So negative pi over 2. Okay, so this was the concept of argument of a complex number, or they also call it amplitude of a complex number. Okay, so let's do a couple of examples, then I'm gonna go over like writing a complex number in polar form in my next video, but in this video I'm gonna go over some examples. Okay, so let's go over few examples. So let's say this example, it says express complex number in standard form. The standard form of complex number is a plus ib. Okay, so they gave you a complex number which is 1 minus I whole square, and they said express this into this format over here. So what are we gonna do? So open this parenthesis here, which is, can use the identity a minus b square, which is equal to a square minus 2ab plus b square. So 1 minus I square can be written as 1 square minus 2 times 1 times iota plus iota square. So 1 square is 1 minus 2 iota, and iota square is negative 1. So this positive and negative 1 cancel each other. The answer will be negative 2i. but they said express this in standard format. So we can rewrite it as 0 minus 2i. So that is the standard form of a complex number. Okay, let's do a few more examples. Let's say we got a number 5 plus 4 iota over 4 plus 5 iota, and they said express this into a standard complex number. Okay, so what we need to do in this case, we're gonna multiply and divide by the conjugate of the denominator. Remember, the conjugate of this complex number is just change the sign to negative sign. So that will be 4 minus 5 iota over 4 minus 5 iota. So we're gonna FOIL the top, and in the bottom we can use identity a plus b into a minus b is equal to a square minus b square. You guys should remember this identity because you're gonna use it all the time in this kind of problems. Okay, so when we FOIL the numerator, let's write it. So we got 5 plus 4i into 4 minus 5i over a plus b. A minus b gives me 4 square minus 5 square and I square. Okay, this is going to be equal to 5 times 4 is 20. 5 times negative 5i is going to be 25 iota. 4 iota into 4 is going to be positive 16 iota. 4 iota minus 5 iota is going to be minus 20 iota square, and in the denominator we got 16 minus 25 into negative 1 because iota square is negative 1. So on the top we got 20. Okay, negative 25i plus 16 iota is negative 9 iota, and iota square is a negative 1, so negative into negative becomes positive, so we got positive 20. The denominator we got 16 plus, so negative, the negative is positive, so 16 plus 25 is 41, and on the top 20 plus 20 is 40 minus 9 iota over 41, which can be rewritten as 40 over 41 minus 9 over 41 iota. See, this is a standard form of a complex number. The first part is a real part, the second part is imaginary part. So this is like a plus bi or ib. Okay. Let's see what else we can do here. Okay, so there is a one of the property, or they call it algebra of complex number. Let's say I got one complex number z1 is equal to a plus iota b. The second one is z2, which is equal to c plus iota d, and they said z1 or z2 is equal to z1. That means c plus iota d is equal to a plus iota b. So when this happens, that means the real part is equal to the real part of the other complex number. So c is equal to a, and the imaginary part is equal to the imaginary part of the second complex number. So d is equal to b. So that is one of the property you can use to solve some examples. For example, we got a problem here. 1 plus iota y square plus 6 plus iota is equal to 2 plus iota into x. and they said find the value of y and x. So what we need to do, first of all, we're going to simplify it, and then we're going to compare the real part with the real part on the other hand side, and imaginary part of the left hand side to the imaginary part of the right hand side. Let's do it. So let's distribute this y square. So y square times 1 gives me y square plus iota y square plus 6 plus iota, and here we got 2x plus x iota. Okay, then we got this is a real value, this is real value. I'm gonna write them together. So y square plus 6, this is imaginary, this is imaginary. I'm gonna write them together. I'm gonna take iota out, common factor, so inside the parentheses I left with y square plus 1 because I took iota out. So iota times y square gives me this term, iota times 1 gives me this term. This is equal to 2x plus x iota. Now compare or equate both sides. See, real part, imaginary part, real part, imaginary part. So we're gonna compare this real part with this real part. So y square plus 6 is going to be equal to 2x, and this is a imaginary part, so y square plus 1, and this x is our imaginary part, is equal to x. So let's plug in this x over here. You know, these looks like two equations which we can solve to find the value of y and x. So let's do that. So if I plug in this x value here, this gives me y square plus 6 is equal to 2 into, and I'm gonna plug in x is equal to y square plus 1 here. So y square plus 1. Okay, so y square plus 6 is equal to 2y square plus 2. Subtract y square on both sides. We'll cancel these out, and therefore we got 6 is equal to 2y square minus y square gives me just y square plus 2. Take out 2 from both sides. We left with the y square is equal to 4. Therefore we got y is equal to plus or minus 2. Okay, then you can plug in this y value here and you can find the value of x. Let's do that. So if y is positive 2, so plug in positive 2 here. So positive 2 square plus 1 is equal to x. So 2 square is 4 plus 1 is 5. So x is equal to 5. Even if you plug in negative 2 here, the square of negative 2 is 4, positive 4 plus 1 is 5. You still get x is equal to 5. So that's the value of x and y. So another type of example that was like find the modulus and amplitude of a complex number. Let's say you got a complex number 1 plus iota over 1 minus iota, and they said find modulus and amplitude of this complex number. So what we need to do? What were the modulus? Remember, if complex number is z is equal to a plus I b, then modulus of z is equal to square root of a square plus b square. So first step is we need to convert this complex number into standard format that should look like real part and imaginary part separated like this. Then we can find a and b, and we can use this formula to find the modulus of that complex number. And then what was the amplitude, which is theta is equal to tan inverse of b over a. We can use this formula to find the argument of this complex number. All right, so let's do it. So whenever you have to convert this kind of number into standard format, there is a denominator. We're gonna multiply and divide by the conjugate of this denominator. The conjugate was whatever sign is here, the opposite of it. So 1 plus iota over 1 plus iota. Okay, so this looks like 1 plus iota square on the numerator, and in the denominator a square minus b square, that gives me 1 square minus iota square. And the top can be written as 1 square plus 2 times 1 times iota square, and in the denominator I got 1 square, and this gives me negative 1, so negative into negative is positive 1 here. So we got 1 plus 2 iota minus 1 over 2. So this one will cancel this one over here. So we're left with 2 iota over 2. So this is just equal to iota. Or in standard form, we can say z is equal to 0 plus iota. So this is your complex number in standard form. And then we can find the modulus. Z is equal to square root of the real part plus square of the imaginary part, which is 1 here, 1 square. So this gives me just 1. So this is the modulus of this complex number. How about amplitude or the argument? So amplitude of z is going to be tan inverse of b over a, which is 1 over 0. 1 over 0. Any number 0 in the denominator is undefined, or we call it infinity. And tan inverse infinity, that is the only case when theta is equal to pi over 2. So that is your amplitude of this complex number. So my next video, I'm gonna make more videos just on some examples. Okay, this video is more of a concept plus example. So that's how you can find the modulus and the amplitude of a complex number. Let's do one more example. That looks like fun. This had 1 plus iota over 1 minus iota raised to power n is equal to 1. So find the least positive value of n that satisfy this equation over here, that makes left hand side equal to right hand side. So what we can do here, so inside the parentheses, first of all, I'm going to change it into a standard form. That is the first rule in these kind of problems in complex numbers. Okay, so 1 plus iota over 1 minus iota, I'm going to multiply by the conjugate of the denominator and divide it by the conjugate of the denominator. Okay, so that is the left hand side is equal to 1. The top gives me 1 plus iota square, and bottom gives me 1 square minus iota square raised to power n equal to 1, right? So top gives me 1 plus 2 iota plus iota square over 1 plus 1 is 2 raised to power n is equal to 1, and I square is negative 1, so 1 plus 2 iota minus 1 over 2 raised to power n is equal to 1. That means this 1 will cancel this 1 out. We're left with 2 iota over 2 raised to power n is equal to 1. 2 will cancel out 2, so left with iota raised to power n is equal to 1. And that is the case when n is a multiple of 4, right? So if n is 1, then it is just iota. If n is 2, this gives me iota square, that gives me -1. That is not equal to +1 here on right hand side. If we plug in n is equal to 3 here, that is going to be again negative iota. How about if I plug in n is equal to 4 here, what will happen? So iota raised to power 4 is iota square into iota square, which is -1 times -1, which is equal to +1. That's what we need. And we need the positive value of this n, which is 4. So 4 is the least positive value of n that makes this equation right. Okay, so answer is n is equal to 4. Alright guys, so these are some examples I was planning to solve. So in my next video I'm gonna go over like converting a standard form of a complex number to polar form or exponential form, or they call it Euler form too. But the motive of this video is to go over the basics of complex number, like some rules, some topics. They might ask questions like conjugate, argument, modulus, or multiplicative inverse. So that's how you can find that's how you can solve these kind of questions. Okay, so thanks for watching the video guys, I really appreciate, and please do share and subscribe to the channel. I'll be making more videos on problems on complex number. That's where I'm gonna solve just problems. That'll be the next video. Thanks for your time and have a good day. Bye bye, take care.